So welcome to the day 2 of our Tau Performance System tutorial for the Admire project. We'll start off by logging into the tutorial sign up page and get an instance. And you can download the slides from this location. Day 2, we will look at several tools today, including Perf Explorer and using Tau with container environments. If you want to install Tau locally on your laptops, please use these instructions. And log into the AWS instance and let's get started. To start with, we just make sure that everything is working well in your web browser setup. And let's start with going to the SRC demo directory, launching a paraprof demo file, and just reviewing what we learned yesterday. So here is my instance, and I will log in. And I go to the SRC demo directory, and I launch paraprof demo.ppk. Let's just try this ourselves, make sure that all the graphics are working properly. And please let me know if you have any questions. I'm monitoring the chat window here, as well as please feel free to unmute yourself. Here is the paraprof main window here, and I can just go to any node, right click and say show thread statistics table, or I can look at a left click and just see the different functions, how much time they take. You can go to options and say, don't stack these bars together. So each function over here has its own space. So you can see how it looks over multiple ranks. Now note that this is the total time across all invocations of that function. This is the time for each colored function. So this is MPI barrier over 20 calls, the cumulative sum, because this is a profile. But if you notice that even though they have a different shape, it's hard to scroll through all these lines and get a view of what's happening for each function's shape. Whereas if you go to the Windows 3D visualization, you can see at once the full shape of the execution. And each function has its own unique shape. And you can see that there are these two functions that are kind of inverse of each other. You can look at the bar plot. You can zoom in using the scroll wheel on your mouse or use the plus minus buttons on the keyboard. And you can look at a particular point in the space by moving the function slider like this, like I'm doing, and the thread slider. So here is the thread slider, and I can reach a point like this, and then zoom into that location and see that on rank 199, it takes 129.5 seconds. In fact, I was asking the developer of this code, Aorsa2D, about why there is one singularity like this in the whole profile, and if it's a problem with the profiling tool. And he said, no, this is a tokamak reactor, and there is a cylinder, and the CPU that gets the central axis that runs through the center of the cylinder has to do more work. And so that CPU is what you're seeing over here, rank 199. And that's why it is unique in the profile. Now, I had mentioned yesterday that we also have a scatter plot. You see, there are many different ranks over here. There are many different functions over here. And we have the exclusive time shown over here. If I look at the scatter plot, what we do is we look at for every rank, we see the time spent in that rank on that function. We get these four functions automatically by looking at their standard deviation. They have the most variation. So for example, a rank took anywhere from 31 seconds in MPI barrier all the way to 260 seconds. That's a wide variation in MPI barrier timing. In the same way, there is a loop over here, and we can see this loop, QL Myra mod. And then there is another function called sigma D. So every rank has a unique value for the three different functions. And also, it has a unique value for this color function. Okay, so you can plot each rank individually as a ball over here and color it using this fourth function. So here I see that there is this one rank that is red hot and all the others are blue or cold. And that's that one function that we saw, which took AORSAT 2D STIX2, which was taking a lot longer on that radial axis. And you can also see some other interesting things, like if you see MPI barrier and sigma D call CQD, and if you just align this like this, you'll see that this is like a diagonal with a correlation coefficient of -1. That means when the time in this particular function increases on a given rank, the time in that function decreases. So just to get started, are you all able to see this and verify that you can look at the data this way? And there is also a topology plot. Here, when you are using a machine like Cray or something where they have PMI, we can see the exact location of the topology of a system. Otherwise, you can create your own custom topology by just clicking here. You can pick the example topologies like this. And these are just Jython functions that correlate a particular color. This is the event that we are choosing. You can pick any other event from this list. You can click here and pick a different color if you want, a different event. And what we are doing is, in this layout, we can then see the x-axis, we can look at the y-axis or the z, and pick different topologies. Like after picking this, I can say sphere, and then I can lay out all the ranks in a sphere, for instance. But
Samit,
it makes more.
Samit, sorry, what you see there is are nodes or what?
Yeah, these are ranks and how they are spatially located for the X, Y, and Z. So there is a mapping that is shown over here. You could pick a different mapping of that with, say, cylinder. But these are just example topologies. It's more interesting when you have a real topology of a machine, so that you can actually see how the mapping takes place of a rank on a particular machine. And here is an example of the Blue Gene system, where we have a topology for this MPI all-to-all V. Now there are 786,000 cores shown over here, but I'm able to see how this all-to-all V function operates on different ranks, and that the lower half of the machine is red hot and the upper half, while running the code, is green to blue in this range over here. Here is another more interesting view from a Cray system where I have PMI. And you see, when I ran this code called QBall on 512 cores, I did not get contiguous allocation of cores on the machine. I got some nodes over here, some nodes here, some over there. They were scattered all around. But using the PMI interface, I can realize exactly where in the physical machine the cores are allocated. And then if I map it in the topology display, I can see how a particular function is spread across the physical topology of the machine. And I can then say that this is the FFTWI no twiddle 15 location in the sample, and it is blue here, there are red spots over there. And in some cases, the topology may matter enough that because you're getting an allocation that is spread out like this, that not all the functions are operating the same way as you expect. So you can see the mapping onto the physical machine. And where that mapping is not available, and if you have your notion of how you want to display it, you could create your own custom mappings. Although it's more beneficial if you get the actual physical layout of the machine through some interface like PMI, and then you're able to show the actual functions as they are located on the machine. So any questions so far with the launching of Paraprof? Do you feel comfortable enough to launch and view this? The way I did this is I clicked on this in topology display, and I picked this example topologies.txt. This is a file, it's just a file in the etc topology directory of Tau. And you can even create your own topologies. And here, I had created one for the sphere, I had created one for cylinder. In a cylinder, if this is a mapping that says for rank R, how do I map it to X, Y, and Z coordinates? And this is just a simple mapping of the topology. And then I can just slice through the X-axis or the Y-axis or the Z-axis and see the average value of that color metric that we have chosen. That is the color here for the loop. So you can see how they are mapped onto the example. In the standard case, you might just see a simple map which just requires a standard mapping. Now, what is interesting is sometimes you might encounter an error in Paraprof. I just clicked that mapping topology and it gave me an error here. This is embarrassing, but what is interesting is you can take this error, cut and paste it, and send it to this email address of Tau bugs. And what is interesting is the way it is designed. Tau is very resilient. That even if there is an error in some operation, it's all multi-threaded. You will find that the rest of Paraprof recovers from the error remarkably well. It does not crash. You will see that I can exit from here and start this window again, and I'm able to operate just as well, even though there was a crash in the application, and all the other things will just still work. And I can just continue to do this, picking another example topology and trying this out. And all the rest of the windows will continue to operate even though there was a crash in the system. So it is localized, it is able to recover, and that's by design, the way we have designed it, that even if we encounter as severe an error as I just saw, and this was of course unintended, this is not part of the demo, that there was a null pointer exception with a invalid map file that I tried to load. I can still continue using Paraprof. So any questions so far before we move on?
Yes, I don't. What's the color scale in the topology map?
Here, let me just bring it up. So in the topology map, it is the time taken in a particular event. So these are the events. You can pick any event that you want.
Okay.
It has taken one event. And then this is the exclusive time. You see, you can pick any other hardware performance counter as well. You could say floating point operations. And then you'll have the floating point operations. And you can see the color scale and I'm saying show the color scale, but this is the name of the loop. The font can be reduced or increased like this. Pardon the overlap. But this is the name of the function that it picked, and you're just seeing the topology map in the X, Y, Z direction of all the ranks mapped in this way. This is by default.
Okay, thank you.
And is the browser working properly for everyone? Are you able to launch the 3D windows and see the performance data properly in, say, scatter plots, bar plots? Yeah, okay, good. Since these are interactive workshops, we do need the feedback. Now let's just go on and try to do what we were doing yesterday, which is first we go to the here. Let me just go to the examples. Okay, so here, just go to the SRC demo co-md SRC MPI directory, do a make over here. And again, this is what we're doing with a simple MPI application. We had compiled it with the -G and O3. And then we go to the bin directory. R.sh is the program. RT.sh is how we run it without tau and with tau. EBS is event-based sampling. And I'll do the RT.sh to generate the profile files over here. Okay. Now, today I want to cover the use of tau's database and how we can run the same example across multiple nodes and generate different core count data and use Perf Explorer using a database with tau. So we saw this yesterday. If we wanted to look at the performance of this application, we saw 8 ranks. These are the 8 ranks. Now you can say paraprof --pack, and then you can give it a name. So here is, I'll say co-md mpi.ppk. So this is what I did. You can also do the same thing. SRC demo co-md SRC mpi make, like that. And then I said paraprof --pack, and then co-md mpi.ppk. Okay. Now, once I have packed the file, I can easily remove all the profile files. Why? Because I have the star.ppk file here. And now I can say paraprof co-md mpi.ppk. So this is how we create a PPK file, a packed profile format. And then I can just take any node, right click, show thread statistics table. Here I see that the application took 21 seconds. I can go down. I can expand this view. And then sort like this and see that LJ forces the function of interest. I can expand this, even go down to the statement level, and then go to the show source code, which will show me that this line of code, which is in this 5-way nested loop, is taking a lot of time in this Leonard Jones computation of this molecular dynamics application. This is the LJ force function. This is the one which takes most of the time. And you can see the loops over multiple iterations. So let me just pause here for a minute and let us try this example again and see how we make the PPK files. And creating these PPK files will be important for our next example. So let me know if you have any problems in launching. So what I did is I removed profile files, and then I did a paraprof, and then this is also very convenient to carry one single file with you instead of a set of files. We also have the ability to create a single file using a environment variable called tau profile format equals merged. And then you can create a merged profile file and load up that single paraprof tau profile.xml. And we'll see an example of this as well. But let me take a minute for everyone to catch up and try this example. I want the goal of this section today is to make sure that you feel comfortable applying tau to any other application. And you are able to choose between different configurations of tau. You're able to launch paraprof and dive deep into where the application is spending its time. And look at the thread statistics table, navigate that. And see, even inside other application runtime system calls and see where it's spending its time. You can see that this is barrier is just waiting. Here you're doing the Open Fabrics interface, poll file descriptors, and waiting over there. So this helps you evaluate what's happening inside system libraries as well. In the case of send receive, let's see what this send receive is doing. It's moving some unaligned elements. It's doing a CQ progress operation. And here's the profile. So just with that EBS flag, you're able to generate all of this information, go down to the function that's hot, and then just sort the results, see where it's spending its time, move the columns around.
Sorry, Samir, a rapid question, if I may.
Sure, please.
How to trust or verify the reliability of exclusive versus inclusive time? Because as you said, it's strictly dependent on the sampling frequency of the event-based sampling.
So in the case of samples, you'll see that the exclusive and inclusive time is the same. It's based on the number of calls that you get over here. It's only in the context of these other functions where you have no context or sample written there, that you have the precise inclusive and exclusive statistics, like in the case of .tau application, for instance. Here I have the timers which are inserted for entry and exit. And then these are used to then calculate the precise timings like you have for here. So if I have an instrumentation in this bar function, and this bar function say takes 25 seconds out of foo, which takes 100 seconds, then I can calculate this region and say this is 75 seconds. In the case of samples, all we get is a particular interrupt. And so what we can say is just that based on the sampling frequency, it collected so many samples at a particular location. And so based on the interrupt interval, the total time taken is so much, which is the same for both of these cases, because this is at the statement granularity. And then this summary node is just a collection of these samples. So you see, this is the number of calls. This shows you how many samples it took at a particular line in the code. The total samples taken outside MPI were 657. Out of those 657, 124 of those darts landed in this particular line of code. So 124 out of the 657, which represents about 19.6 seconds of total time, gives you an idea of where the application is spending its time. Sampling is basically getting some samples in the code, but it's not 100% accurate. As you can see, between this T5 and T6, it missed this region of code where samples were not taken. But there's a good chance that if your application is stuck in a barrier somewhere, no matter what sampling period you choose, you'll find that it will collect samples over there, and it will point to that region of code as being an interesting region that you should explore. Did I answer your question?
Yeah, perfectly. Very clear explanation. Thank you.
Oh, great. Thank you. And are you able to generate the performance data, generate PPK files like this? Do you feel comfortable in the use of Parapath?
Yeah. I've succeeded in
doing this. Okay, good. Let me again take the other example, the example that we saw with, say, Zoltan. And in this case, all the libraries that it needed were based in a Singularity container called ecp.simg. So even if I had the Zoltan binary, if I do an LDD on this, you see it is missing many of the libraries here, as the ePetra libraries are not found. And the reason is that they are all in a container. To recap, we saw that yesterday that in a containerized environment with E4S, you can build a large collection of software, and it uses SPAC as the package manager. And there are many different products that are already available to you. If you just say, say Singularity run and say ecp.simg. So all I did is cd to the Zoltan directory, and then I said Singularity run ecp.simg. And then I will be in a environment where I can run a C++ application where all of these packages are available to me in the form of the SPAC installed packages. And then I'll be able to just do a run operation on this like this. It will run the application using, so I am here in the pwd here, cd to that directory. I can say run.sh and run.sh like this, where I'm again using this Trilinos framework, and then I'm running the tau exec-ebs on Zoltan. Okay, so this is running this complex C++ application, and then it's running it with tau. Now here, if you see just the output, this is the output with tau. Total time taken is 3.35 required by ML. And if I go up and see what it was without tau, instead of 3.35, I see that the total time was, oh, well, it was actually a little more. So 3.35 was 3.58. So the overhead of the full application run with tau was insignificant. but I get profile files like this. I can see the paraprof display and see the time spent in individual functions at the statement level. And I can also create a tagged profile file. Now note that in this case, paraprof is actually running inside the Singularity container. And I'm able to see the time spent at the function level and go down to the actual loops and see exactly which block row multiply function is taking how much time. So if I take this line and say, show me the function bar chart, it will show me this line at this CPP file, and it will demangle the names. I can also see the 3D graphics from within the Singularity container running paraprof through there. So here it is. And what do I do to create a PPK file? I can just say paraprof and say zoltan.ppk, or say zoltan4p.ppk like this. And if I remove the profile files, I can again run.sh. I could, for example, run it by doing module load trilinos and then say MPI run-np8 CPUs, tau exec-ebs zoltan. So what did I do? I was in this Singularity container. I said module load trilinos. And then within Singularity, I said MPI run-np8 tau exec-ebs zoltan, like this. Okay. And here I can say paraprof packet in zoltan 8 processor.ppk. Okay, so first I ran it on 4, then I ran it on 8. And then I can say paraprof zoltan 4p and zoltan 8p.ppk at the same time. So I can now pick up multiple profile files and load them at the same time. This is 8 CPU run, where I can see the thread statistics table. And then there is the 4 CPU run, and I can see the thread statistics table. Now, what is interesting is that you can also take a particular node and say, add this thread to the comparison window. So I go to the node 3 and add thread to the comparison window. And I have this, and then I can look at node 3 here and add it to the comparison window. So you can see the difference between a particular location of how much time the solver took on 4 or 8 processors and so on. So you can compare multiple of these ranks by just adding them to the thread comparison window. So I did a click on rank 3, and then I said add thread to comparison window like this. And this is over here in this region, right click, add thread to comparison window. If you don't have a mouse with the second right click button, you can always go to Windows and then go to thread and then go to a particular window like this and look at the function, bar chart, and so on. But here is the add thread to comparison window. So what we covered here is how to create PPK files, how you can have multiple experiments and load them and compare the data between multiple experiments in paraprof. I'll take a minute for everyone to catch up and see if you are able to run the experiments in this way. So can you try this Singularity, run it, at least even if you have the same profile file, you can always say paraprof Zoltan 4p.ppk and compare between two different nodes. You could say add thread to comparison window here and add another thread to comparison window here. So you can compare node 0 with node 2, the two MPI ranks, and see how they differed in the load across a key solver over there. Any questions so far in what I just showed?
Yeah, well, when we click on the show thread statistics table, that's a flat profile, isn't it?
It is, it is. You can also create a call path profile, but here it is
there is a hierarchy. You have the Tau application, and but that's not the call path. I don't see the difference.
So here it is just a collection of samples that have been added to the, so sampling always allows you to create, so there is a call path profile as in a full entry exit based instrumentation based call path. And then there is this sample, and we have just added up all the samples collected in this particular region to create a dummy node called summary to give an overall idea of how much time is spent in that whole function. It's just a collection of these samples, whereas the other call path that you're referring to, let me just show you. The other call path that you're referring to is the one that we generate with entry exit instrumentation. And in that case, you see over here, if I had inserted hooks at the entry and exit of every function using, say, source instrumentation or compiler based instrumentation, then I get a flat profile, but I can turn it to a call path and say call path depth of 100. And then I see this entry exit based instrumentation without any samples. That's a full call graph that is shown over here. Now, if you and if you use this again with what we just tried with, say, Zoltan or one of these applications, you'll see that the MPI functions then are inside the Tau application, but they may not be inside the instrumented part because there is no instrumentation in the rest of the code. We are just using sampling like this. So there are these samples that are collected. Is that okay?
Yes, thank you very much.
So you are comfortable with creating PPK files, launching one or more PPK files, and comparing the performance of one node with another in this segment, right? So I'm going to exit from the Singularity container. We'll come back to this later. And let us go and see another tool called Perf Explorer. Perf Explorer is a tool that allows us to compare different runs. So I have exited from here and I'm back over here, and I can say cd to the src demo, and there's a data directory. I'll show the slide here. Using Perf Explorer. So in this particular project, it's really important that we look at performance databases. And here we see the perf DMF framework, the performance data management framework. We call it Tau DB now. And we have the ability to export the profile files into a database which can have different backends. You see, we want to create queries such as show me the exclusive time spent in MPI barrier across multiple ranks, the mean exclusive time, and maybe compare it with MPI barrier timings when I ran it on 2 processor, 4 processor, 16 processors, and compare one particular MPI barrier performance. Now, these are high-level queries, and we want to shield the user from the complexities of SQL. SQL is a very powerful structured query language used by these databases, but it can be very complex for our developers to use this directly. So we have a layer called Tau DB, which shields the user and then provides a graphical interface to the Tau DB. So here, you can have a different backend. You can have PostgreSQL, H2 from Apache, MySQL, DB2 from IBM or Oracle, and then they all speak different dialects of SQL. You know, banks spend hundreds of thousands of dollars in converting applications that use, say, one database to another, like DB2 to Oracle translation, because the SQL is slightly different, and so your application needs to be ported. But using this layer of Tau DB, you are able to target different backends while maintaining compatibility with some performance evaluation tool APIs. So with that, we look at how we can create PPK files, and typically you run a job, you pack the profiles, you create multiple of these, you can configure the database, configure Perf Explorer, and then either manually add the trials or use a upload script. In this case, we are going to use a workshop via HPS data directory. And there, we will have a script called upload.sh. And what this will do is it will take canned profiles that we had created on 2, 4, 8, 16 processors and upload it to a database locally on this AWS. So we'll create a full database on AWS instance. We will upload the data to that. We'll launch Perf Explorer. We'll click and expand this database tab. And I'll first expand the DB2, the H2 database, go to all applications in this NAS parallel benchmark, and then select this experiment scaling like this. And then go to the charts and then pick some canned charts and show you how to use this tool. So let's go to CD. I'm out of the container, that's important. I'm going to workshop VIHPS. And then data. I have 2 directories here. One is on Scorpy, one is on Tau. Let me go to the Tau directory. And these are the PPK files. They are files that we had created from a previous experiment. And all I'm going to do is say upload.sh. This is the upload. You can see that it does the configure with the H2 database. It does the Perf Explorer configure. It uploads the trials to the database and then gives it a name like this and takes the PPK file one by one in a for loop and just puts it in the database. So what did I do? I just said CD to the, as shown on the slide number 161. Here are the instructions. And I'll do exactly this. CD to slide 161. Workshop VIHPS data Tau, and then say /upload.sh. It's downloading some Weka files for data analysis. It's uploading the data. You see it uploaded 8.ppk over here. And then if you were to use paraprof, you can actually be in a different directory. You don't have to be here. I'm in, say, a different directory here where there are no profile files. And I can just say paraprof without a profile file. And now you see there is a default H2 database. I can connect to this database, and paraprof will be executing the SQL calls, but you can see all trials, application, experiment scaling, and say NAS parallel BT benchmark. I can double click on this, and I can double click on this time, and I have loaded the file, not from the file system, but from the database. I can see the stack bars together. I can go see the window, 3D visualization, bar plot, the same as we did before, but everything has been loaded from the database now using paraprof. Okay, so here is paraprof comparing looking at the profile for 16 processors. And again, how did I do this? I went to the paraprof in any other directory, and I just say, open up this key of H2 database, expand this application, this trial, and then load this by expanding this and double clicking on this green ball, which is time. That launches this. I can then see this, and I can see the time spent in various routines for the 16 processor profile. I can open up two at the same time, like this, and open up this and this. Like I could compare this thread to that thread. So is this okay? What I just did is I just uploaded the data to this directory. I said paraprof, and I then expanded a database entry. Expand the default all trials BT MZ B.16. It's the same interface, but I'm executing SQL calls to load the data in paraprof. Are you able to try this with the upload and launching of paraprof? I'll wait a minute for everyone to catch up. And then we will launch Perf Explorer at the same time as paraprof. And you can see that concurrently we can access the database that we have just created by uploading these profile files. And then we'll be able to evaluate the scaling properties of this run as the second application. So once again, what I did is first I started with the workshop VIHPS data tau directory after exiting from the Singularity container. And I just did a upload.sh. And then I launched paraprof. And I can expand this database like this and see the scaling experiment and load any of these profile files directly.
Is there a difference between Perf Explorer and Paraprof? Because in the slide
Yes.
you
There is a difference between these two. Here I'm typically looking at the full profile of an application. In Perf Explorer, I'll launch this Perf Explorer next. And it will also connect to the database concurrently. See, it shows you that it's connected to the database connection successful. And here, you can do a lot of data analysis on performance data. I'm opening up this H2 database. Then I'm opening up this NAS parallel benchmark and the experiment for scaling. I'm going to select this scaling so that it takes all these 4 trials underneath it. Then I'll go to some canned charts like this. So now my focus is on this particular experiment where all these 2 through 18 processor profiles have been loaded. I'm going to the charts and let me say, show me the total execution time. I have loaded the data, the mean profiles for all the different core counts, 2, 4, 8, 16. Now I'm saying, show me the total execution time. Now what happens here is that we are making a query. We are saying, show me the inclusive time for the .tau application, the top level timer for different core counts and issue a SQL query to the database. Then we get the results and then Perf Explorer charts that. So here is the total execution time. And you can see that the number of cores as it goes up, the total execution time based on the total threads of execution. Okay, there are probably 4 threads in each of these experiments. You can see the time decrease like this. So this chart was created by Perf Explorer by using the SQL queries using the TauDB layer. And regardless of which database I have on the backend, whether it is H2 or Oracle, I can use the same queries and have a single code base for Perf Explorer to interact with the TauDB layer so that it can read the profile data from the SQL. So we maintain a set of the compatibility so that we could switch the layer of the actual database while still keeping this. Now, H2 is a very versatile database. We have found that it scales well with the experiments that we are using. It comes from the Apache Foundation. And the best part is that it is a file system-based database. You just created this in your own instance. You didn't need to open up any ports like you would do with MySQL or any of the PostgreSQL databases. And you don't need a full database administrator to manage the whole backend databases. You just are easily able to use a file system-based database that's maintained in your .paraprof directory. So there is a .paraprof. And it maintains a file system-based database in that directory. Okay. So again, the steps are go to the workshop via HPS data tau directory, do upload.sh, Perf Explorer, click on this, and then pick some charts from here. And here is the Perf Explorer. I have opened up this. I open up this application, experiment, and click here so that these 4 experiment or trials are selected. And then I can go to charts and say, show me the stacked bar chart. And here I see the time spent in the different code regions and different core counts, number of processors. I can say, show me the aligned bar charts. And here, each function is in its own space. So I can see how this do operation on OpenMP did. And here is an OpenMP profile. And I can see exactly what that looked like. This is a very powerful tool. You can see relative efficiency. It asks you whether it is a strong scaling or weak scaling. In this case, it's a strong scaling. I say okay, and it shows me the relative efficiency. I can say relative efficiency for by event, and it shows me for all the events. Or if I wanted to pick a single event, I could say, show me the relative efficiency of a particular event. And MPI bcast, and then I look at it and you can see the efficiency. And if you look at other charts that we have, there is group percentage of total runtime. There are groups. I'm saying, show me the MPI group, and I can see the total experiment. I'm creating these charts. I can even create custom charts. This is very interesting. I can create my own SQL queries and say, I want to chart this on the x-axis, this on the y-axis, create a chart for me. Say, for example, if I say the number of cores is on the x-axis. So I say cores, and I choose the value, say threads of execution. I say the y-axis should show me the mean inclusive time, or say the exclusive time. And I say not just main, but show me all the functions. And I say, well, let me just pick some functions, say matmult substitution, matvec substitution, and MPI barrier and bcast. These 4 functions I'm going to pick, and I'm going to say exclusive time. And the chart is scaling. And I can just say apply over here. So I'm taking the 4 functions from the database. I'm saying I want x-axis to show the number of threads of execution, y-axis to show the exclusive mean time, and then I apply it like this. And then I see this 4 functions, and it created the SQL queries for me and allowed me to create a custom chart like this, which I can then save as a vector image like this in EPS or SVG format. And I can pull this into a LaTeX file and just store it. Or I can also save it as a JPEG file, or sorry, PNG file like this. So if I don't like the distance between these, and I say I don't want I want them to be all equidistant, I can redo this. I say show me categorical x-axis and say align the x-axis labels, create a different chart like that. So I have 8, 16, 32, 64 equally spaced. But what I'm trying to get at is I can store data in a database. I can extract it in Perf Explorer and chart whatever I want in a custom chart by putting it on the X and Y axis. I can also add metadata to the application. I could have application data that's stored with the performance data that can show up here, and I can pick that value in the X and Y axis value for the metadata field. And then I can chart that. So you have the ability to do this. You can do a lot more with Perf Explorer. We should take some time and explore this tool and allow everyone to take a few minutes to connect to this and try this experiment. So I'll take, let's take the next 5 minutes to try this workshop via HPS data tau, and then do the upload.sh, and then launch Perf Explorer, and then expand it to bring it to this particular region and launch this. I'll just wait here to answer any questions you may have and see that you can also access it through Paraprof.
Yes, Samir, two questions. Can I
Yes.
do this with any PPK? So
Yeah, any PPK file, absolutely. You just
Path
upload
Explorer,
any
right?
different core count PPKs like we created with Zoltan. You remember we created the 4P and 8P PPK files, and then you can just upload anything you want into the database. You can give it an application name, an experiment name, and then you can run this. I just used some canned data so that it's easy for you to just see it, 2, 4, 8, 16 PPK files and upload them to this particular database that you create and run this. I've had many users who have a huge hierarchy of their application with different runs on different platforms, and then they can compare scalability of one with the other. And it's a good way of working with data rather than our usual way where people write an application, they add hooks to a particular code region, then they do some MPI all reduce operation and get the timings for that run, and then cut and paste that time in a Excel spreadsheet and then chart it with X and Y axis like this, and then take a snapshot and then try to get the pixelated snapshot into a LaTeX paper or something like that. Here, everything is automated and you can just pick and choose the data along X and Y axis for custom charts and create your own views for the data.
Yes, so for the custom chart, I don't know, but I tried what you tried, and for me, the interval events seem empty. Could you please
Okay,
repeat
let
how
me
you?
try this again. I'm connecting to Perf Explorer after the upload has happened. You have done the upload, right?
Yes.
Now you see this JDBC at the top. Did you expand this? Did you see the application NAS parallel benchmark?
Yes, everything is experiment scaling. I clicked on it.
Experiment
And
scaling, okay. And then this worked properly for you? Like if you said
yes,
aligned stacked bar chart, you can see this data?
yes, this did work.
Okay, so just keeping this scaling experiment here, I'm now going over to custom charts. Now I'll open up X-axis value and pick threads of execution. Okay,
Yes, I did.
I did this. Then I clicked, I said something like threads. Y-axis, I called it, say, inclusive this time. Okay, and here I click this main only and uncheck it. Now I see all of these events. I
Okay.
can click here and multi-select, say 3, 4 events like this.
Now it's working.
And yeah, and then I click apply over here. And now I get these 4 and I can create the chart. Does this work now for you?
Yes, unchecking the main only did the trick.
The
Basically.
main only, okay. Otherwise, it's just main that you do have at the highest level. Are others able to create the charts like this and see some of these other interesting views? Like this is the runtime breakdown view. Charts runtime breakdown. And here, I'll see how each function is running at different core counts and what portion of their value is adding up to, say, the 100% of the total execution time. So you can see at different core counts how your application is doing for different code regions. Again, this is selected and go to charts, runtime breakdown. There is a lot more to this tool, including correlation analysis between events. You can do correlation analysis, you can do cluster analysis with k-means clustering, and do the visualization. But let us start with just custom charts and the charts that are canned that will allow you to do, cross-experiment analysis. And I want to spend this time talking about the databases because in our Admire project, we will be evaluating databases. We'll be looking at how we can store the performance data in a database, and having access to something that's already implemented with storage with databases may help us choose other options for storing data and using it with tools like we have got here. And what I like about the H2 database here is that I can bring it up very easily without much involvement of the system administrators, and I can have file system based database which supports locking, and I can have two or more tools use the database at the same time. So I can have Perf Explorer up in the window as well as Paraprof using it. Any other questions? Are you able to do this hands-on session with the Perf Explorer? The instructions are right here and on slide 161 and in the chat window. Here's visualizations. I can pick a particular metric and then I can do distribution of significant events and charts like this with the visualization, create data summary. I can look at the data summary here. I can look at normal probability plot. There's a lot that you can just use with even launch Weka with this data set. Histograms. This is the histogram view. So take some time to explore this tool. You may find that it provides a lot of features that can help you with data analytics with performance data with just this scanned data set. So for doing these views with the visualization, I picked a particular metric over here, like this time. And then I can pick this visualization and do this. And then you can even pick clustering method, dimension reduction, clustering, inclusive, exclusive, correlation analysis. And it queues it, it's doing the correlation analysis. This can take a long time. So any comments? Are you able to launch these charts properly? Are you able to create custom charts? Are you able to look at just selecting a metric like this and going to visualization and picking create histograms or box chart? Are you able to create such charts or canned charts like these? Good to hear, Alberto. Is anyone having any problems with either the AWS instance or launching of these tools or running this workflow? I want to give you all some time so that you can try these things, and trying it once yourself will be much better than any PowerPoint slides that I can show with different views. And feel free to unmute yourself if you're having any issues. It's hard for me to gauge how everyone is doing on the tutorial. Should I continue with the rest? Do you want some more time to work on this? Well, there are a couple of other things I wanted to cover about using Tau with a full application. And let me just minimize this while it's running the clustering analysis and get back to this. So let's take a full application and try to run this with Tau. I had mentioned yesterday about how we can create Docker and Singularity containers. I had showed how you can run the Zoltan application with different libraries loaded. Now I wanted to also mention that E4S has a build cache. So you can, instead of installing packages from the source code, you can install packages from a binary build cache. And we have build caches with over 50,000 binaries of applications. So let me show you a full application. And this is Nalu Wind. It's a wind turbine simulation code, a CFD application. So I'm going to the Nalu Wind demo directory over here. And let me just say SPAC find Nalu Wind. Okay. Now here, it shows me that it is installed, the Nalu Wind application. I could say SPAC location -I Nalu Wind, and it will show me where it is installed. Okay, it's in this directory. If I looked inside this directory, ls and say bin, I'll see the NaluX executable. Now, instead of just using this, let me delete this application and build it from the build cache. So I can say Nalu SPAC uninstall Nalu Wind. So this application will be deleted. It says, do you want to proceed? I'll say yes, and I'm deleting this application. So here is the spac.yaml file which shows how to build this application. This is a recipe of all the dependencies that are here in this environment with MPI. And I have a number of packages. I say you want to build Nalu Wind with FFTW, with Hyper, and use all of these things with release with debug info as the build type. So this will put the -G while building it. But instead of using the source to build it from a scratch, I'll say SPAC-E, the environment directory is current directory. So it picks up this spac.yaml file from the current directory. And then I'll say install. What this is going to do is it will look at the build cache. It will look at all the dependencies that are here on this AWS image. And now it's fetching this file from the build cache directory on AWS. And then it will install this binary. Now, Nalu Wind is part of the Exawind ECP application. And they are, it's a very complex code. It can take over 4 hours to build it from scratch using the source code. And here we are just building it from the build cache as a binary. So I've installed it. It's installed again. So now I'll have, if I say SPAC find Nalu-wind, it will find this. Okay. So here is a demo.sh file where I'm running this code with tau. Okay. In this particular directory, it goes and runs it with tau. And I'll just say /demo.sh. I should probably have not done this at the same time as it is running this experiment because I have 8 cores. So there may be some interference, the performance data, but let's just run this at the same time. And I'm running this. It shows me what are the files over here. And you can see over here, CD Nalu wind demo. Okay, here, cat demo.sh. I'm going to go here, and then I'll cat run.sh. Here is how you run the application. You run it as MPI run np8 nalu-x after loading the SPAC load command, and then give an input file as edge hybrid fluids.yaml. And then it takes all of these output files and merges them. From many, you get one EPU. And then tau run.sh. Run tau.sh. Here, in this case, all I did was added the tau exec-ebs. In this case, I'm also creating a merged profile file, and I'm turning on call path and call path depth to 100 and creating this. So now I will run it on 8 CPUs using this tau exec-ebs. Instead of this, I am using this. So this is the original code. This is the tau exec-ebs. And then I turned on these call path and profile format merged. Instead of getting 8 files, I'll get a single file. And then I'll launch Paraprof with this tau profile.xml file like this. Okay. And if you want to see what's happening in the AWS instance, I'm actually using 100% of all the cores to run this. Now, this takes about 3 minutes. Even the smallest problem I could find, it takes about 3 minutes to do this CFD simulation in this real application. But I wanted to give a feel for using tau with a real ECP application instead of just benchmark programs like NAS parallel benchmark. So I hope you are all able to do this. This is slide number 188. And I did the CD Nalu wind demo, and then just did a demo.sh. Is this okay? Are you able to try this example? Maybe this is a good time to take a break so that we'll take a 5-minute break and let everyone launch this demo.sh so that we'll have performance data when we get back, and then we can view it in Paraprof. It does look like my correlation analysis completed in Perf Explorer. And I could see the correlation results over here. We get back. Here are the correlation results, where I can see pairs of processors and compute RHS with compute RHS with verify. So these are all the 16 or 64 cores, and you can see the correlation result is over here. And there it has completed. And it should have created an output.e file. Before going on the break, let me just look at the output file and launch ParaView. ParaView is a third-party graphics browser and a visualization tool. It's a very sophisticated visualization system. And we'll look at the output from ParaView after we come back. So let's take a 5-minute break and let everyone try this. Is that okay? We'll come back in 5 minutes. Okay, I'm back. I hope you can see my screen properly.
Yes.
Okay, good. So what I did here is I ran this CFD application. It took about 3 minutes and it created output.e file. And I have ParaView loaded in my environment. And I just launched ParaView output.e. Now, in case you're getting confused about ParaProf, Perf Explorer, and ParaView, ParaView is not a performance evaluation tool at all. It is just a visualizer. And I'm looking at the output of the application. I want to see what the application did and visualize that. So there is some fluid flow over a plate that we will look at. And to do that, I'm going to check these 3 boxes. There's a pressure box, there's a turbulent viscosity, and there's a velocity box. I'm going to check all of these boxes, and then I'll click on this green button that says apply. So I'm clicking here in ParaView, and there is the plate on which we are looking at the fluid flow. Again, I'm not an expert in CFD. I'm just looking at the output of this. I will look at VTK. Let me go to velocity. Then let me go to pressure. And instead of surface, let me say surface with edges. I can zoom in. Let me just expand this. I can zoom in like this. I can rotate this. This is a full plate. It has all of these elements. Here is the point Gaussian. You can see the 3D plate. I can look at other views of this data. But you should be able to first select velocity, then go to pressure. And you should also be able to click on play and run the view over here in ParaView. Let me just log in here again. Launch this ParaView browser. And you can see over here, click play, and you can see how the pressure changes on this plate. So this is just a quick demo of what the application was doing. This is the surface with edges. I'm clicking pressure here and clicking play just to give a view of what the simulation did in the output on the 8 CPUs. So this is a very simple problem. There are other more complex problems that they are looking at where there's a whole wind turbine and they are coupling 2 codes. One is the AMR wind for the wind flow, and then the Nalu wind for the near body wind turbine. And then they are using these wind turbines over the water and moving the entire turbine as the flow of air goes on. So those take exascale systems, the exascale class systems where they are running these simulations in this simple AWS 8 processor instance. The problem that we could solve in this with 90,000 of these edges is just a simple problem where we are doing some fluid flow, and then we can look at the pressure by clicking this button, and you can see the pressure over the course of simulation. So are you able to run this code? Can you run the demo.sh? Are you able to run the output.e with ParaView? You can click these 3 buttons, click the apply button. First select the velocity, then select, say, the pressure, And here is the surface with edges. And you can click this and you can see how the pressure changes with the edges. I just thought it would be more interesting to show the performance data for a simulation and actually show what that simulation was doing in a visualization tool. Now, typically installing all these packages is a big headache where you have to get the 3D graphics working properly with all the underlying components with, say, ParaView with the dependencies. And E4S helps you with that, whether it is Visit or ParaView or a number of data and visualization tools such as HDF5 or Adios 2. They're all pre-installed in the containers that E4S provides. So as we look at the data analysis and IO libraries, you may find that a lot of software is already pre-installed in this AWS instance, either through the container or directly in the E4S image. Yeah, so please feel free to unmute yourself. I would like some feedback. Were you able to run this NaluWind demo.sh, go to this directory, this NaluWind directory, and then launch something like ParaView output.e, which is created after the code runs. Is someone? Yes, go
Yes,
ahead.
it works.
It works, Clement. Great.
Yeah.
Are you able to launch ParaView and then look at the pressure like this with velocity and pressure, and then look at the surface with edges, click the play button and see the variation of
Yes,
pressure?
I just click the play one.
Point Gaussian. Here is point Gaussian, and you can see the CFD simulation with the pressure over that. Are there experts in CFD in this call? Are there people who have used ParaView before?
I've seen ParaView. I've seen it used. I've never used it myself, but I've seen it used in geology.
Oh, okay. Very good to hear that. I hope you find this AWS image useful with all the tools pre-installed and being able to run everything within a web browser. Well, this is the ParaView demo. We are not looking at ParaView for this particular Tau tutorial, but I just wanted you to have a feel for what simulation does. And then we look at the Tau output. Here I'm closing this ParaView and I'm launching tauprofile.xml and say paraprof tauprofile.xml. And here is the profile data that's generated on 8 of these CPUs. Now, again, I can look at the 3D visualization. I can see how each of those ranks was doing. Here is the bar plot, scatter plot, and you can see the function and the thread slider like that. But let me just go down to the thread statistics table, say, move the stack bars together and bring down this thread statistics table. This time I had used the call path equals 1, and I used the call path depth equals 100. So we get the real call path. And here, what I did is I am running this application. This application uses Cocos. And we saw the Cocos profiling interface. And here, You saw the push pop regions we saw in Cocos, that you can have an interface where you can have a parallel for like this. Okay. Here you see that there is a parallel for, and it has a first argument that you can use to encode what this lambda function in C++ is doing for sending the work over to pthread or CUDA or other runtimes. Cocos is an API for node level parallelism, not internode but intranode. And so you can specify what each of those operations does, and then it shows up in Tau's paraprof with the exact name. So this is the same name that we are seeing in the application. And you can see that there is one Cocos thing, which is operation op star X. There is the Belos pseudo block GMRES solution manager, total solve time, 100 seconds over here. You can expand this. You see what happens. And this is very interesting because what we see here is the way the application developer encoded the different parts of the solver in their understanding of what's going on. So you can literally read the profile in terms of English. You can see that there's an orthogonalization step, there is a operation star X, there's a precision star X, there's a applying of some Chebyshev in some LF pack, and these are the parallel fors, and also wait all for MPI. And you can see what MPI wait all was doing when it was stuck there for 27 seconds. So in 27 seconds, 22 seconds were just wasted in the global poll operation over here. So there are things like this that can show you where it's spending its time and what it's doing in this entire operation. So you can see exactly which Cocos application function call is taking up all that time, and you can see how it does on different nodes. So all of this time is wasted in the Belos pseudo block GMRES solution manager when it is doing this preconditioning star X, where it applies a Chebyshev and calls MPI wait all, which then goes to do polling, waiting for the messages to arrive. Any comments so far? Do you see the such breakdown in your case? We can also look at other parts of this code. There is the inclusive time. Here I'm looking at NALU preconditioner, MuLu preconditioner setup time. You can see all the parallel for operations. Here is a context where we see the setup time. And I can, look at a Cocos operation over here, sort it, and look at specific parts of the code. And you can see first argument is very useful over here for the application developer, as they can, without any change to the binary, you can get detailed information with using the Cocos profiling interface in this manner. So There's a lot of data over here. Here is COCOS parallel for. I can go down and see this entire application information. Here is a function bar chart. Now you can see this is a parallel for operation. This NALU assemble edge solver algorithm in the run algorithm, and then the C++ templates. And finally, it goes down to this one line of code, which is tpetra linear systems.c at line 1138. Here is another Sierra NALU execute. Just see. And I can jump right to the source line in this run algorithm. So here is the momentum edge solver algorithm execute. And this was the line of code that took so much time. So with event-based sampling, you can jump directly to the location, even in a complex algorithm, and see exactly where it's spending its time in this full call path. But what is interesting is you can just see exactly what the application is doing and go down to the MPI all use and see where it's spending its time. If it's taking 10 seconds, out of those 10 seconds, you can see MPI all reduce was just polling for 8.3 seconds when it was called along this path. So here you have narrowed down and said it's taking between 7.1 and 10.6 seconds in just polling in MPI all reduce when it was called by the Belos block pseudo block GMRes solver manager with Belos over. So, any comments? Were you able to generate the tau profile.xml file with this demo.sh?
Yes,
Yes.
but I don't have the polling slowdown, I think.
Oh, you don't? You know, I was running that Perf Explorer algorithm for, I had only 8 CPUs and I was running that Perf Explorer correlation analysis in the background, if you remember.
Yeah.
Maybe that affected the whole computation and it got a little imbalanced.
Yeah, it's faster overall on my my instance, I mean.
It is faster, right? Okay, so I had only 8 CPUs allocated in this instance. And so you can even see that it's a little different. My 3D graphics view may be different from what you got. But it's good to know that you were able to run this code and you were able to generate the profiles and see the output of the application in ParaView. Now, in case you are wondering about this this container that we showed earlier and said, you know, is it, how would this work if I had a HPC system and I had just this ECP.SIMG? You know, I did the Singularity run ECP.SIMG, and then I ran this this code like Zoltan, which uses Trilinos, using all the libraries inside the container. Even the MPI was inside the container, right? We created this in the Zoltan directory. We did a clean.sh, we did a compile.sh, and then we created the Zoltan binary. Now, I ran this with tau inside the container using the MPI that shipped in the container. All of these libraries were built using mpitch. Now, if I'm trying to deploy this container with all the tools on an HPC machine, I'm not using the mpitch. How would I use this container with all of the tools that are in there, including HDF5 or Adios 2 or Cocos, with my MPI that's running on my HPC system, right? So we have a tool that you may find useful in using such a container. And that tool is called the E4S Container Launch Tool. So the goal of this is that applications that are built with MPI in the E4S container should be able to use the MPI that's there on the system. And you can replace the MPI in the container with the system MPI. So that if you were using a fast inter-node communication library, you want to use the native interconnect, but you want to still use the libraries that come from this E4S container. So the application and data are external to the container, but the compiler time libraries and tools are inside the container. And we can replace the MPI with the mpitch ABI compatibility layer using a tool called E4SCL. And we can also replace the application with OpenMPI, the mpitch with OpenMPI using a tool called Y4MPI, which comes from CEA in France. And we have integrated this with the E4SCL so that you can build a binary once with the container and run it unmodified on all the HPC x86 64 clusters. So to do that, I'll actually show you how this E4SCL tool works with this Zoltan application and replace it, the MPI in the application with the system MPI. Okay. Here I'll try two different MPIs, maybe three different MPIs. One will be the Intel MPI, and the other will be MVAPitch2. The third is OpenMPI. So to use this, you just need to tell it what is the backend, whether it's a Docker or Singularity, and say initialize the E4S container launch tool with the Singularity. This is the image. When it brings up the image, what are the startup commands that you need, such as module load Trilinos or SPAC load Trilinos. And so you can give a startup commands over here, the container image, and then the Singularity. And then E4SCL does the hard part of figuring out which libraries need to be replaced and how the whole replacement. And you can just say E4SCL with your MPI run command, and it will run that application. So to show this replacement, this is how the whole E4SCL system works. We will follow the commands on line 193. Here, I will run the E4SCL with the container. So first I'll go to the Zoltan directory, I'll do clean.sh and then compile.sh. Compile.sh creates the Zoltan. Okay, if I do a module load Ilinos and do an LDD on this Zoltan, I'll see that there are many libraries that it loads. In fact, it loads 41 libraries. And if I look at there is this mpitch library that it's using. So we ran this code. We are familiar with Zoltan binary. Now, instead of running this binary inside Singularity with this MPI run, I'm going to come out of the container. I'm out of the container. I did an exit. And now I will use run E4SCL.sh file. Oh, sorry, I'll go to the Zoltan directory and cat run E4SCL.sh. So here I'm using the Intel MPI, and I'm going to use the one API installation on this AWS. I'll say E4S CL init, use the backend of Singularity. This is the Singularity file. Here is the startups commands. And I'm saying stack load Trilinos at the beginning. And then I'll use the MPI run from Intel MPI to load it. I'll just run it like this. And here is the E4S-cl.sh. So please try this yourself. You'll see that I'm loading up the one API over here. And then it will take some time to do the investigation with Intel One API, figure out which libraries it needs to mount in the context of the container and how it must do the substitution. And all of that is hidden from you. It takes care of this, and it will just substitute this MPI with this MPI run with the E4SCL. And we'll be able to use the one API. So the target launcher, this command is coming from here with MPI run. And you can see this is the MPI run it's using. It finds 15 libraries and 10 files that it must use. And because we are using MPitch ABI substitution, we don't need to use Y for MPI. And here is the Singularity backend. And it will run after mounting all the files correctly. It will use the MPI run to run the Zoltan. Now, it has to load up all those 41 libraries. It has to change the MPI and substitute. But finally, it should be able to run the application after this initialization step. This initialization step takes time for it to figure out and mount everything. But then the subsequent MPI run operations are fast. You are using the speed of the Intel MPI, and it's running the application. As you see, it ran it pretty fast, 2.4 seconds. You remember it was like 3.6 seconds inside the container with the MPage. So it's using the native MPI on this system. I will try another run E4SCL, and I will this time use, instead of Intel MPI, I'm going to use MVAPitch2. MVAPitch2 with the EFA AWS driver. So I'm going to do a which MPI run. So that is the only change I made. I just uncommented this and commented this out. So instead of Intel, I'm using MVAPitch2. And I say run E4SCL.sh. So you can see this is the E4SCL container launch tool. And this message is coming from MVAPitch2. It says it could not find libxpmem.so intranode transfers. Now it's finding 19 libraries in case of MVAPitch2 that it has to substitute. And then it will run this same application over here. This ran in 3.1 seconds, still faster than the container. So it's using MVAPitch2 in this case. And now I'll show you how to run the E4SCL with Y4MPI using OpenMPI. Here I'm saying from MPage substituted and use to OpenMPI and run this MPI run exactly with the module load Y4MPI. And then here, I can say E4SCL Y4MPI.sh. So here it just says Y4MPI is taking care of all the substitutions and the libraries. This is a very complex operation. You have a binary, a Zoltan binary that uses Trilinos and 41 other libraries. And you are saying, please substitute the mpatch in the application binary, without modifying the binary, please use this ympi directory and use this MPI run and do the substitution and run the application on 8 CPUs or 4 CPUs. And here it took a little longer with the substitution. So I just showed the same binary being used with Intel MPI, with MFAP2, and with OpenMPI. And if I say module load Y for MPI, maybe in a different window. Then I can go to this directory. To the etc directory and look at the Y4MPI config file. And here you can see that you can substitute from one MPI to another using Y4MPI, which is like a switch. Here is the mpatch, here is the default OpenMPI that it knows the location of that OpenMPI. It can even handle Intel MPI and MFAP2 as Y4MPI for substitution, but in our case, E4SCL does the work for doing the substitution directly with mpatch ABI. So you don't have to translate the calls using Y4MPI. But MPI requires such a substitution. So I'll take a moment to ask any questions on what we just saw over here. Do you have any comments? Are you able to run these tasks like this? Maybe take a minute for everyone to try this. The overarching goal here is that if you take this container image, which has libraries built with MPI, then you can just use your system MPI with this E4SCL tool, and you can take a single binary for a complex application and distribute it in a binary form so that anybody can use the binary with the container using Singularity while using their own high performance MPI implementation that is native to their HPC cluster. And you can have MFAP2, Intel MPI, system installed Intel MPI or OpenMPI and still use the same binary. So you can now distribute your complex application, which uses libraries from the container, in a binary form, and that will run on multiple HPC systems.
What's the link between Tau and E4S?
Tau is included in E4S as a tool, and it's part of the containers that E4S distributes. So we can do the performance evaluation of codes like we just did with Zoltan using Tau installed inside the container. So if you were having an HPC system and you just downloaded a single file like this, ecp.simg, from the E4S web page, then it will already have Tau built for many different GPU architectures in it. So you don't have to build it yourself. It's already pre-installed inside the container. You can use it to instrument programs inside the container. You can use it with different compilers, including Intel compilers, NVHPC compilers, and others, and even create binaries that can then run on your HPC machine using the system MPI. using the MPI that's outside of the container. That help?
Yes, yes, thank you.
But just to get this clear, you have to reinstall the application inside the container, right?
Yes. The application is outside the container. The application is not in the container. The application is in my home directory. I did the clean, I did the compile. The container was just used to provide the libraries like Trilinos that the application used. And then I came out of the container with this exit. And then I ran the application. I can run it inside the container using mpeg that's there in the container. But I can substitute that mpeg using this E4SCL with the system MPI. So I use it with Intel AI, with MFAPH2, and then finally OpenMPI. Did I answer your question?
Yes, thank you.
Are you able to run this workflow? Were you able to run the E4SCL with, say, OpenMPI and Intel MPI? Yeah, good. Okay. There is also one more interesting thing that I want to show you, which is I showed you that you can take an uninstrumented binary and you can launch it with tau exec-EBS. And we used that throughout the tutorial. In fact, we never changed the source code or the binary of any of these applications, right? Now, what if you wanted to change and use the compiler to add hooks to your code? What if you wanted to use precision instrumentation and say, I want to not parse the source code, I want the compiler to add hooks, but I only want to instrument certain functions in the code, then what can I do? Here is a tool that we can use for selective instrumentation with the LLVM or Clang compilers. Now, the Clang compilers take a lot for us to install it. It can take a lot of time to install it. So we'll use the Singularity image again, where the Clang compilers are pre-installed. I'll take a simple example. I will use tau to instrument it and use a filter file like this. And then I will run the application. Okay. So let me just show you how I can do these steps. This is slide 189. I'm going to use the Singularity container because it already has LLVM pre-installed in it. These Clang compilers, the latest Clang compilers, and we have a tau plugin. What this plugin does is it allows you to selectively instrument code. You can use code instrumentation tools with compiler-based instrumentation, but they sometimes add a lot of overhead for C++ codes, because if you instrument one file and it pulls in, say, vector or map, standard C++ library file, then all the functions, including constructors and destructors, get instrumented. That adds a huge overhead when you instrument whole code. With event-based sampling, you can narrow down the focus to specific functions. But what if you want to instrument main and then solver and then function A and function B and nothing else? How can I do that? So I will show that using, here is a application. And if I say, if I say make clean, make, here I'm instrumenting the code with the PDT parser and source instrumenting everything. Okay. and I create a binary and I can run it. If I run this with matmult and I launch paraprof, I have done source instrumentation. So here is the master, it's doing a wait, and here are the worker tasks that are doing this multiply matrices. So this is a Fortran program, and I can do source instrumentation. This is just an example to show how this may work. But I'll go to a C example. In this case, I'll do a make clean, and I'm going to do an MPI CC. And I create a binary like this. Okay, there is no tau in this application. This is uninstrumented. Okay, and I can run this like this. This is a C program. So I showed you with Fortran a source instrumentation, and here I'm using an uninstrumented binary, a C application. Now we have seen that it's very easy to insert hooks into this by just doing tau exec-ebs and running it. And it's doing a matrix multiply application. I can say paraprof and load the performance data. Here is node 1 thread statistics table. It says that it took 1.7 seconds in the application outside of MPI calls. With sampling, I cannot explain full 1.73. I can explain 1.67 seconds out of 1.73 seconds using 56 samples. And I can expand this. It says there are two functions. Is a compute interchange function. Compute function took 1.07 seconds. Compute interchange took very little time compared to that. What I'm doing here in the code is something very trivial. I have a compute function where I do a matrix multiply operation with ijk, and I'm doing a Cij plus equals aik bkj. And then I'm calling compute interchange where I do ikj. So this runs much faster because the cache is aligned very well with the way the application runs. So if I wanted to instrument this code, I can do source instrumentation, I can do compiler-based instrumentation, but let me use a selective instrumentation with LLVM and demonstrate this. So what I'll do, I'll first do Singularity run ecp.simg. And here I'm going to the src demo direct. Okay, so I'm doing a cd src demo for matrix multiply, and then I'm going to do the Singularity run ecp.simg. Now here I can do a module load LLVM DOE, and here I have a Clang compiler, my path. This is the latest version of the Clang compiler, version 13. You can see Clang version 13. With this, we will have a tau plugin that I will load. Now, I had showed before that I can do export tau makefile equals $tau make. Let me see what makefiles are there. You see all of these makefiles? These tags are based on what we support in that configuration. Here is the Clang compiler with MPI and PDT. This is with kubectl. We don't have any GPUs here, so I'll just use this one, or I can use it with Python or without MPI or Intel level 0 or HPC for NVIDIA or ROC Profiler with AMD GPUs. So we have support for all 3 GPU architectures in this Tau. I'm going to use this LLVM and say export Tau makefile equals this. Next, I'm going to pick Tau options. You know, if I say Tau cc.sh help, I can see all the options. And here are the options, Tau cc.sh. I have one option which is opcomp inst. This is in the Tau option that I can set like this. And I'll set a filter file. So I have a filter.txt. There's no such file. Let me just create a file and say filter.txt. And I say begin exclude list of compute interchange initialize end exclude list. Okay, so I have created a filter file. It says don't instrument the compute interchange and don't instrument the initialize function. Then I can say Tau options are opt comp inst for compiler based instrumentation, Tau select file equals filter.txt, and also turn on the verbose so I can see what it's doing. 3 things I have selected. I said use the compiler to instrument my code, but I'm going to specify a filter file that can cherry pick just the functions that I want to instrument for precision instrumentation. And I'm saying exclude these 2 functions and instrument everything else. So here, I'm not cutting and pasting because sometimes from PowerPoint, transferring this, the single quotes get messed up. So I'm typing it all out. And then I do a make clean. I do a make build over here. So it is using LLVM. And you can see over here, it is using the plugin using compiler-based instrumentation. And it passes the filter file with the F plugin. Here is the Tau profiling.so. Here is the file manager. The input file is filter.txt, and it creates the .o. So what is interesting is that we have a plugin that's going inside the intermediate representation of the compiler. It looks at the abstract syntax tree, it looks at the expanded instructions inside the compiler, and then it does this precision instrumentation at the function boundaries. And it has this filter file that it reads, and everything is being by the Clang compiler with our plugin. And you can see that it excluded these 2 functions and it found the exclude list. And then it did this for the other file, initialize, and then it created the executable called matmult. So there are no, I'll remove all profile files. There are no files. I can say MPI run matmult, and it runs this, and I can load this and see here, these are the functions that were instrumented. You don't see compute interchange, you don't see initialize, you see only compute. Okay, there's free matrix, there's allocate matrix. I could have done something else. I could have said, I just want to do instrumentation and compute interchange, but I don't want do work, I don't want initialize. I just want to look at these 2 functions. And in that case, I would just alter the filter.txt and say, instead of exclude list, I could just comment all of this out and say begin include list. end include list. I can't type, I have typos. And I can say just instrument main, compute, and compute interchange. Okay, just an include list, nothing else. And here, if I do a make clean and make again, it says include functions, and these are the functions that it will use for creating the executable. If I run this, here, I ran this, I can run paraprof again. And now I see the time taken in main compute and compute interchange. And so I can look at a particular function and add the instrumentation hooks just for that particular function, and then create a binary that is with optimized instrumentation. So in any case, if you would like to try this, you can try the tau makefile like this and see the filter file, add these functions, and pick and choose what you want to instrument. Here is another example, filter.txt. I can say I want to have compute and initialize. And that's the initialize call here. So I still think that while source instrumentation and compiler-based instrumentation are viable tools, the easiest way to use tau with most of these applications is just to use the tau exec-EBS, which remains a very popular way to run these examples. Like if I have demo and the NAS parallel benchmark, make clean, make sweet. Sorry, npi run-np4 lu. Then just running it with tau exec-EBS. Will in most cases be the default way to use this. And then of course you can use the IO flag like that and generate performance data at the IO layer, the POSIX IO layer. So please try some of these examples. And here is what I just showed. And then paragraph. And then you'll be able to see both the thread statistics table, and you'll be able to see the context event window for seeing which files it read and how it handled it. Like here is a file that it wrote to, and it read these files. It wrote out to standard output total of 2,300 characters. So at this stage, I would like to take any questions that you may have. Can you try some of these examples? Maybe take a few minutes for everyone to try the Tau exec and there are quite a few capabilities of Tau, including Perf Explorer, that you may want to look at. There is clustering, correlation analysis, custom charts. There's a lot to cover with Tau. But I just wanted to give a feel for what is possible with the use of Tau exec for looking at the I/O performance, compiler-based instrumentation, using it with containers, and then also mapping the data and using the Perf Explorer tool to look at the performance database. So there's a whole lot of material here to cover, but I would rather if you try some of these examples yourself and see how comfortable you feel. And please feel free to reach out to our team. Jean-Baptiste Bénard and I are always here to answer your questions. And let us know how we can help you with using Tau for the performance instrumentation. We will keep the AWS instances running for a little bit. And then if you have interest in trying this out some other time, please send me an email and I can bring up the instance just for you. And you can try any kind of instance, even in Europe. And we have the funds to start up AWS instances where everything is pre-installed if you'd like to spend some more time on this. Any comments, please? This is a time for anyone to unmute and speak up about the tutorial.
Well, no, it's just a comment, but thank you for the tutorial. And I had a question from my team, so I guess now I'll be able to answer some of them regarding Tau. So thank you.
Oh, good. And you were able to run some of these examples properly, and things worked.
Yes, I tried the filter list.
Okay, good.
And it does work. I do have the cone graph.
And did Perf Explorer work as you expected?
Yes, I haven't tried the last thing you've shown, but I've tried it before and it worked, yes.
Okay. Well, I hope the use of, we covered quite a lot of territory with starting from just profiling with Tau exec-EBS all the way to using the performance database and using with the container. So there's quite a bit of material that we try to cover in this small period. And I'm sure there may be some questions that you may have later. So feel free to reach out to us and tell us how we can help them. I would like to, yeah, go ahead.
Yeah, regarding the containers, do you recommend the use of containers?
So that's a very easy way to get a large amount of software installed on your system. So, you know, typically what you will do is you will want to install a library like HDF5 or Adios2 or some other IO library. You'll need some compression tools. You'll need some tools with MPI and compilers, whether it's LLVM or Intel compilers or Intel MPI or GPU support. And you waste a lot of time in just finding the compatible versions and getting everything just right to fit your application needs. And with containers, you could just download a single file, even if it takes a couple of hours to download on a slow connection. You can just launch with just a singularity, and you'll have everything set up in a way that that you could, you know, use. So there is some compelling arguments to using that. And especially if you're using Python, we have found that containers can actually, because they don't have the overhead of Lustre metadata, you know, file system naming issues, they can be very fast in some cases.
There's a tool that we use that's developed in France at INRIA. It's called Geeks. It's based on the Nix package manager, and it's
okay.
It covers some of the same uses. It's a different architecture. I couldn't tell you more. I don't know it very well.
Okay, well, I encourage you to explore the SPAC package manager and all the other tools that we are using, including the Y4MPI that's developed at CEA in France. We also have a OVA file, which has many of these container runtimes that you can download. It has the same login password that we used here. And you can see more about it. A lot of the Tau development work goes on at the Performance Research Lab that I direct at the University of Oregon in Eugene. And finally, I'd like to take a moment to thank our sponsors, the Department of Energy in the US, the CEA in France, the EuroHPC Admire project, the Department of Defense, the National Science Foundation, NASA, and our partners in various institutions, including University of Oregon, the Ohio State University, the developers of MVAP-H2, ParaToolSync, the developers of tools like Tau Commander, Tau, and the University of Tennessee, Knoxville, the developers of PAPI, TU Dresden in Germany, the developers of Vampire, and Jülich Supercomputing Center, the developers of tools like Scorpy that are used with Tau. You can download Tau from these locations. We have VirtualBox support for Tau, as well as containers from E4S that you can download. And I have some slides for reference that you may look at towards the end in this slide deck. So please let us know how we can assist you. And I look forward to working with you.